Muy bien. ¿Estamos bien? Okay. First of all, I would like to introduce the rest of our team. So if you are only now joining y hablas español, por favor, busquen la sección de interpretación. It's a little globe, and you can choose your audio and
En
change it
donde
to
dice
Spanish.
más, los tres puntos.
Los
Ajá.
tres puntitos. Where it says more or más, and you
Ujú.
can go into interpretation. Okay. The other thing that you could do is enable your closed captioning. So the closed captioning, if you go to the section that says captions, you can enable it, and it will be able to show you the language that you are speaking and then the language that you want to hear. So if you if you would like to see the closed captioning in English, you can select that. If you want to see the closed captioning in Spanish, you can select that, and it will give you the option to see real-time translation. So what's great about this is when you hit the captions, it'll show you the option of view full transcript. So it'll show up on the side so you can see the full transcript. So right now, you would be able to see me speaking in English, a translation in Spanish, and if you are a learner that is supported by audiovisual learning, then you will be able to hear it and see it and look at the content of the speaker. Okay. Okay, Mouse. All right. It seems like we have ended the big influx of folks for now. And I haven't introduced myself. My name is Nidia Asaf Aragon. I am one of your hosts. I'm going to spotlight the rest of our team here so you can see them. Ayelen, if you could share your video. Okay, this is Johansel Villalobos from the CNSA. En unas palabras, Johansel, tenemos a Johan Carvajal. Déjeme encontrarlo.
In Spanish or English? Well, no, I'll do it in English. No,
Whichever
thank
you
you. Thank
want.
you for having me. And this has been a ride. Thank you, Nydia, and all of the organizers. Johan.
Hey, hello, my name is Johan Carvajal. I'm Associated Professor at the Costa Rica Institute of Technology. I'm leading a local initiative on quantum computing. And with Nidia, of course, we are delivering this to all of you, and we are very glad to have you here. So welcome and start learning and never stop.
Yes, thank you, Johan. And we have Karime, Dr. Bergman, who's going to be speaking shortly. I think I lost Johan's video here. Oh, here he is. Okay, so just want to make sure that you are able to see the team. Also, for all my interns, if you have your video, please turn that on. So there is a lot of work that has gone into bringing this event together. One of our main goals was to try to bring quantum computing to as many people as we could. So the reason why we are providing real-time translation in Spanish, both through an interpreter, both through AI-generated captions, which it has a pretty penny on that, but we are happy to provide it if it's going to help reach more individuals, is because for us, knowledge and education is an equalizer that is going to allow us to create generational wealth. There's a lot of opportunities that are out there in an emergent field as quantum computing, and we really want you to take this opportunity to just explore the field. It is some of the concepts are can be a little cumbersome, and so they can be somewhat challenging if you approach them from an angle. We are going to try to not scare anyone with big equations. Just know that the goals here are that you're gonna walk out of here learning, well, virtually walk out of here, learning what a qubit is, how to write a quantum code that is going to be simulated and also be run in a real quantum computer. You're going to learn some of the basics of Python and how to illustrate things, how to run some simulations, plot things of what quantum circuits are doing. You're going to see how a quantum circuit looks like with different simulators. So you're going to see the difference of a regular circuit, and you're going to see that. We're also going to talk about different gates, different algorithms, and hopefully by the end, you will see that some of these different things can be applied for businesses. They can be applied for you to continue your education. We're going to talk about quantum machine learning, and we're going to talk also about some of the opportunities that are out there for you. So first and foremost, please make sure that you join the Discord channel, which is where we're going to be answering our live questions. If you haven't already, please join the Discord channel, accept the rules or reglas, and once you do that, you'll be able to see our live questions section. Ayelen, would you like to add anything there? Would you like to share what it looks like so we can see that? Ayelen is our admin in Discord, jack of all trades.
Sí, ahí me pueden escuchar.
Okay.
Perfecto. Sí, cuando entren van a ver solamente 3 canales, los cuales son reglas, rules and welcome. En reglas tienen las reglas para leer y aceptar los términos de convivencia dentro de Discord. Están en español, y dentro del canal de rules las van a encontrar en inglés, las reglas para aceptarlas. Así que, por favor, vayan, lean detenidamente, y al aceptarlas van a poder ver todos los demás canales que se crearon para el evento. Así que cualquier consulta pueden escribirme a mí por privado, por Discord, o ya plantearlas directamente una vez que acepten las reglas dentro de Like Questions.
Okay, thank you very much, Ayelen. And I just want to share a quick summary of what we are going to be reviewing for the event. So this is your kind of like attendee guideline. Just a little bit about Qiskit, right? It's an SDK language. You need to install, if you're going to work with Conda, right, you could do that, install Qiskit, install Python. If you are an absolute beginner, please just work with Google Colab, and we were happy to answer your questions on how to do that. Everyone who is on the call should have received your welcome email. Your welcome email shows you how to access Google Colab. It not only shows you how to access it, it also walks you through the different videos step by step. So I can share that also. It's a couple of videos within a Google Drive. So remember, we're going to be getting together here Wednesdays, 8 p.m. EST, 6 de la tarde en Costa Rica y México, y 9 de la noche en Argentina. Again, if you have only recently joined and you speak Spanish and you would like the real-time translation, go to the 3 dots at the bottom of your screen, hit the little globe there, and select audio in Spanish. Very well. We are going to be kicking off this week with the absolute basics. and Dr. Bergman, who's on the call, is going to walk us through some of the quantum computing aspects, and he has some really creative examples. When you are looking at the different states of these examples, remember that they are mathematical equations explained in a way that you are going to be able to process the flow of what it is that for a quantum state to be in probability, a probabilistic aspect, rather than the misconception that is Schrodinger's cat dead or alive. You would understand that it's a matter of probability, and that we observe these states is that we know we're able to see whether it is within a sphere, right? The black sphere that he's going to cover also. So let's talk about next week. So we're going to have assignments, right? We're going to have certificates, awards, assignments every week. They're due on Sunday. And we are not going to be doing exceptions. Please be on time. You have until midnight. Saturday, we're going to have some office hours. Friday, we're going to have some office hours. We're going to walk you through that calendar in a minute. And Discord is where we're going to have all communication. No one should ask you for any personal information whatsoever. This is an entirely free. Esto es completamente gratuito. Nadie tiene por qué pedirle ninguna información. I would recommend that you keep conversations public. So in the Discord channels, ask a question. We have interns, mentors, organizers. We have a lot of people that are here to support you. If you do not understand, if you're feeling that something is a little complex, ask questions. We have so many people that are eager to help you. The first couple of weeks tend to be that moment where you're breaking through a wall of understanding. This could be hard, mostly because it can ask us to think differently. And so if you're just willing to go with it, to do the exercises, you can earn certificates every week. And we will, for the IBM challenges, you will have a challenge winner certification also. And we have a lot of great potential learning paths for you within IBM, also where you can earn a LinkedIn badge. They just came out with some new information that I'm going to make available to you also. Code of conduct, please be nice. Just be nice. We have a lot of cross-cultural individuals here, and it is very important that we understand that in certain cultures, direct communication, especially when it's not your first language, is absolutely needed, so there is no misinterpretation. So si usted habla español, sea directo, por favor, para que sus preguntas sean entendidas. If you speak Spanish, please be direct in how you're asking what you don't understand, so things could be better understood. And just if you want to the link is embedded here, so you can review IBM's code of conduct as well. And then just congratulations to all of you here. It takes a lot of courage to try to learn something new, and it takes even more courage to be willing to fail until you succeed. So congratulations for giving yourself this space and this opportunity. And with that, I'm going to stop sharing my screen. I have so many other things to do, but in between the different speakers, I will give you more information so we can get right to it, and you can let your brain rest and just know the way that we've designed this is content, get a little bit of break, you can ask questions, and then we're going to keep going with different concepts. So Dr. Bergman, if you are ready, I will allow you to share here.
Sounds good.
Awesome. Okay, should be ready for you to do.
Yes, here we go.
Okay. And oh, I would like to, I'm sorry, Kevin, let me introduce you here 1 second. My bad. Actually, I'm gonna take this presenter thing from you real quick. All right, so Dr. Kevin Bergman is a physicist specializing in sensors measurement techniques, and he has worked on everything from next generation carbon nanotube photodetectors to consumer robotics, and is currently seeking the next chance to apply scientific knowledge and problem solving skills to scientific and engineering challenges. Fascinated by physics, he was a child. He's delighted to be able to bring some of that joy and wonder to others by making complicated physics topics comprehensible. And he and his partner live in the Bay Area with their 2 cats, who often help him study quantum physics by putting themselves in boxes. So Kevin, go right ahead and share again. Thank you for that. Sorry for not introducing you before. And you are good to go.
Okay. Yeah, so welcome everyone. As Nini mentioned, is the screen sharing still going?
You can do that again.
Okay. It's currently telling me I don't have permission.
You should be able to go.
Host disabled participant screen share.
Try it again, please.
Zoom is doing something strange. Zoom knows. Ah, there we go. Okay. I'm still getting
Sorry.
host disabled participant screen sharing.
Okay, so let me do this. Can someone else try to share something from the hosts, from the co-organizers?
Oh, and it just suddenly started working again.
Awesome. Okay.
Okay, can you see this?
Yes.
Okay, good. So yes, welcome. As Ninia said, I'm going to be trying to help you understand kind of the basics of quantum physics that you're going to be using in quantum computing. So, okay, good, here we go. So I'm going to be doing this in kind of 3 chunks. First, I'm going to talk about just some of the differences between quantum physics and classical physics. Basically, how is quantum physics different than just the way we see the world around us working? Then I'm going to go into what's known as Dirac notation, which is essentially the main way that we actually write down quantum physics and that we actually kind of put it into equations and work with it. And finally, there are a few quantum concepts that are going to be useful for you to understand that you'll see frequently in quantum computing. And it turns out these are actually pretty straightforward to address with Dirac notation. So we'll cover those as well. So first, I'm going into the differences between classical physics and quantum physics, between what quantum physics says and kind of your physical intuition, how you've always seen the world work. And that's going to be divided into these 2 sections here. So the first difference between classical and quantum physics is that classical physics is deterministic and quantum physics is probabilistic. So let me unpack those terms a little bit. Let me elaborate a bit. So let's say we take kind of the classic physics example where we start with a ball and we just fling it. So classical physics tells us that as long as we know a few things, if we know the angle it's fired at, if we know the speed that we throw it with, and we know a few other things like the strength of gravity, then we know every single point that that ball will pass through during its flight through the air. And we can also tell you exactly where it's going to land and exactly when that's going to happen. And this is what deterministic means. By knowing the initial conditions, we can determine every single part of this trajectory. Quantum physics, on the other hand, does not work like that. Quantum physics is probabilistic. This means that it can only give probabilities of outcomes and paths. For example, if in quantum physics we wanted to get the location where the ball lands, we would not say it lands at this location. We would only be able to say something like there's a 70% chance it lands here, a 10% chance it lands off to the side in one of these two places, or a 5% chance it lands in either of these two places. And we would not actually know which one of those it is until we actually throw the ball and then measure it afterwards. And before we measure it, it's in what's known as a superposition. It's in every single one of these states simultaneously until we measure it and collapse the wave function. And this can apply to basically every parameter. It's not just location that is probabilistic, that can be in a superposition. It can be velocity, it can be energy, it can be all sorts of things. And this is actually part of what makes quantum computing so powerful. Since a quantum computer kind of samples multiple states, it can do more powerful computations than a classical computer. So the other main way that quantum computing, that quantum physics and classical physics differ is that in quantum physics, everything is a wave. You may have heard the statement that light is both a wave and a particle. Well, it turns out that once we start working quantum physics into things, this is true of everything. Everything is a wave and a particle. And for matter, that wave indicates probability, like we were talking about with our probabilistic quantum physics. And so the main thing that this brings into play, and the source of a lot of quantum weirdness, is that waves have something called interference, where they can interact in much stranger ways than you would expect just from seeing the world around you. So here on the right, I have some examples of interference. So first, let's start with constructive interference. We have these two waves down here, which are absolutely identical. They have the same wavelength, they have the same amplitude, same everything. And so we can add these together. And here we have the peaks align with the peaks, the valleys align with the valleys. So we get one wave after adding them that is twice the height of the two component waves. And this makes sense. 1 + 1 = 2. But the weird thing about waves is when we start looking at some other cases. So down here, I have what's known as destructive interference. And here, again, we have the same two waves that are perfectly identical. The only difference is here we shifted one of the waves to the side. And so now each peak lines up with a valley, each valley lines up with a peak. And now when we add these together, these cancel out. And actually we get nothing, we get 0. These waves have destroyed each other. This is known as destructive interference. And so actually waves, when you add them together, can be anything from 0 to 2 times the wave, if the wave is identical. And this is true for quantum particles too. Particles can interfere with themselves and each other and have much more complicated behavior than you would expect from just seeing things in the world around you. And again, this is one of the principles behind quantum computing, that you can have much more complicated states and much more complicated interactions between quantum bits, because essentially you're introducing an entire new dimension here. This phase, this degree of offset between the waves determines how different waves, or even the same wave, will interact. So this is all very interesting, but at this point, you may very well be wondering, is this actually real? Like, is this the way the world actually works? Or is this just kind of an explanation physicists have come up with that kind of describes the math, but isn't really the way that the world actually is? It's just some abstraction. And well, the answer is yes. We have actually proven, we have done experiments to show that all of this is the way the world works when you get down to the quantum level, as weird as it seems compared to our everyday experience. So first, let's start with this whole thing about particles actually being waves, about quantum saying everything is a wave. Well, even in classical physics, light is a wave, and there are very classical experiments that show interference with light, that prove that light is a wave. And it turns out you can completely replicate these with quantum physics. You can take electrons, you can take atoms. The largest thing I'm aware of is people have done these experiments with whole viruses, but basically you can take chunks of matter and do the exact same experiments with them and get the exact same results of interference of wave nature. Now, I don't have time to go into this, but if you want to look up more information on your own, the phrase you're looking for is the double slit experiment. That's kind of the classic experiment that shows interference and the wave nature of particles. And then the other thing I've discussed here, and a thing that often seems very hard to accept, is this idea that particles, that anything really, according to quantum physics, is in a superposition until it is measured. That you can't actually say the state until the measurement happens here. It's undetermined. And so you could ask, and in fact, this was a debate between physicists for decades after quantum physics was developed. Is the state actually undetermined? Is the particle really in every possible state? Or is it just that it's in one state and we just don't know what it is? For example, imagine I flipped a coin and I caught it and I covered it without looking at it. You know, I can tell you the probability of that coin being heads or tails, but generally we would say that that coin is in a heads or tails state. Like under my hand, it is either heads or tails. We just don't know what it is yet. And quantum physics says, in contrast, it's both at the same time until we look. And which one actually is it? Well, it turns out that there are experiments where you can distinguish these two possibilities, that people have actually tested it and measured it. And the world works in the way that when quantum physics is relevant, states genuinely are not determined until they are observed. Again, I could do an entire lecture on this, and it's a very interesting topic, but I don't have the time to get into it here. So for more information, you want to look up the phrases Bell test or Bell inequalities, as Bell was the name of the physicist who determined that you could actually distinguish these states. So this is the quantum versus classical comparisons. And so what are the takeaways from this section? So the first thing I want you to remember is that quantum objects are probabilistic, not deterministic. Until you actually observe something, until you make that measurement, you can only state the probabilities of being in certain states. And the thing is actually in a superposition of all possible states. The next thing to remember is that quantum objects are represented by waves, and they can interfere with themselves and other objects. And in particular, they have a phase that's kind of an additional dimension compared to classical objects. And finally, something I just want to point out, the type of quantum computer you use doesn't really matter for any of these physics. There are quantum computers out there based on everything from superconductors to electrons to atoms. They're just all different ways of accessing the same physics. It doesn't matter when you're programming a quantum algorithm. In the same way, it doesn't matter what computer you're working on for regular programming. They're just all the different ways of running the same sort of thing. So that covers kind of the introduction to some of the oddness that goes on in quantum physics. And so next, I want to tell you about Dirac notation, which, as I mentioned before, is the primary way that we are going to actually be expressing quantum physics, that we are going to be writing it out and solving it. And so before I get into the details here, I just want to cover what is my goal for this section at the top. And what I want you to walk away from this having is some kind of understanding of what's going on here. Essentially, the thing about physics is that every statement, every equation in physics is actually a statement. It is telling you something about the world, either the way the world works or the way that the world is. And so what I want to do here is to teach you to read Dirac notation to know what it actually physically corresponds to. And this will make everything easier to understand than if you're just having to look at as just kind of a pile of math. So with that said, I'm going to be splitting this up into several parts as shown here. So the question here is, how do we represent quantum physics? And so we're using Dirac notation, or what's known as bra-ket notation, as an alternate name. And so we start with this by we take a bracket and we split it in half. So when you split this in half, you're left with the first half, a bra, and the second half, a ket. And the C, I guess, kind of gets lost in the middle. And so each of these states, each of either the bra or the ket, represents a single state of an object. And later we'll also see that unifying them back into a complete bracket has some meaning as well. And so there are a lot of examples I could use for this, a lot of kind of traditional ones used in quantum classes, but I don't really want to overload you here. I don't want to have you trying to understand qubits or understand subatomic particles or any of that while you're also trying to figure out this new notation. So instead, I'm going to be using something that's, I think, a little more intuitive. We're going to be doing quantum physics on cats. If you've heard of Schrodinger's cat, then you know that cats are also quantum objects. We can make them obey quantum physics, but they're much more intuitive than electrons. We have an idea of what a cat will be doing, how it will be behaving. No one really knows what an electron is doing in its spare time. So let's get into it. I would say that most scientists who have studied cats would agree that a cat has three possible states. They might be eating, they might be sleeping, or they might be causing trouble. And so we can represent these with a cat. We can represent any state of any object with a cat. So here on the right, I've put together our three cat states. Here's the sleeping state inside its cat. Here's the eating state. And here's the trouble state. And these are kind of what I'm going to be calling the basic states of a cat, meaning that essentially these cover everything that a cat can be doing, and they're mutually exclusive. No matter how much it might want to, a cat cannot sleep and eat at the same time. So once we have these basic states, we can start putting them together into more complicated states. So for example, what if we want to know what a cat is doing at specific times during the day? Well, we can just look at our cats, observe them, and we see that this specific cat we're trying to describe, during mealtime, it has a 75% chance of eating and a 25% chance of causing trouble. And if we look during nap time, we see there's something similar, but with sleeping. And if you know cats, you know that they always have a chance of causing trouble. So let's put these together into a state using cats. Well, the general rule here is if you want to define a composite state, a more complicated state, you can just add together your basic states. So here we've just added together our eating state and our trouble state to make our mealtime state. And then the general rule here is then you multiply it by the square root of the probability of being in that state. So since there's a 75% chance of the cat eating during mealtime, that means we're multiplying it by the square root of 3/4. And so basically, putting that together, we have our two mealtime and naptime states. And this is making a statement that is exactly the same as this statement here. If you can read these, it says what we're saying up here. And now these are quantum cats, so they're in a superposition of eating and trouble simultaneously. But otherwise, this is saying the exact same thing. So I've said multiple times that measurement is very important in quantum physics. And so the question is, how do we make a measurement now that we know how to formulate our states? And one of the places you might want to use this is if you have a completely unknown state and you want to start probing it to understand it. Well, here's where we complete the bracket. You perform a measurement by essentially adding a bra to a cat. And the way to understand this, the message that this is saying, the question is asking is, if I am in the ket state, if it's currently nap time, what is the chance that the cat is currently sleeping? And for various reasons we're not going to get into here, the actual probability is the square of the bra-ket pair, but essentially this is the question that it's asking. And if you're familiar with complex numbers, with imaginary numbers, this is actually the complex conjugate square. But if you're not familiar with them, don't worry about it too much now. We're not really going to be getting into that. So we can formulate some basic rules for our basic states. Remember, I mentioned that these are mutually exclusive, or the physics word is orthogonal. That means that if we have two different basic states in the bra and the cat, then we have a 0% chance of being in both of these states. So for example, if a cat is eating, the chance that it's sleeping is 0. And then not just for basic states, actually for any state, if you're asking what is the chance that something is in the state it's in, if it's in state A, what is the chance it's in state A? Well, that's 100%. It is always in the state that it is in. So that gives us our other rule. So then if we want to apply this to composite states, we can just start applying a bra to a composite state and then propagating through. So let's go back to that question I asked at the beginning. What is the chance that during nap time, a cat is sleeping? Well, we take our sleeping bra and then we substitute in our definition for nap time in terms of our basic states. And now we're just multiplying. So we multiply through and we get two bra cat pairs, two completed brackets. So we have a sleeping sleeping and a sleeping treble. And now referring back to our rules for basic states, sleeping treble goes away, that's 0. And then sleeping sleeping is 1. So this comes out to square root of 3/4. And then when we apply the square to get the probability, like we said before, it's 3 out of 4, it's 75%, which is exactly what we should be getting from our original definition of the state. So this is how we do a measurement. Now, this is good, and this is useful, but I have a way to make it better. The way to make it better, the way to make anything better, is add more cats. So what if we want to describe multiple cats? What if, say, we have 2 cats, cat 1 and cat 2? Well, here I've defined an arbitrary state using the Greek letter, which is very popular among physicists. And I'm basically saying here with subscripts what cat 1 and cat 2 are doing. So this is saying that cat 1 is currently eating and cat 2 is currently causing trouble. And something that you'll see very frequently is this method for kind of compacting everything into a single cat. So basically what we've done here is we've abbreviated the first step, each state by their first letter, and then we just combine them into that cat, and their position in the cat tells us which cat it is. So here's cat 1, here's cat 2, they're eating or causing trouble. And I just want to call ahead to where you'll see this in quantum computing. You will see this used very often to represent the state of qubits, your quantum bits that you'll be working with. So this is essentially saying the first qubit is 0, the next 2 are 1, the next one is 0, and the next one is 1. And again, you know which one it is by their position in the cat. And then once we have this, again, it's just multiplication and addition to form composite states. If we want to have an eating state and a mealtime state, now we can just multiply through and we get the eating pair and the eating trouble pair. So this is most of Dirac notation. This is most of what you'll need to describe the quantum state of any object. So to kind of summarize, to give you the takeaways again, a ket or a sum of kets is a method of representing the state of any object. So right here, I have kind of a generic cat state where we've got all 3 of the states that a cat could be in and the probability of being in any of them. And here I've used them to describe the state the sun could be. It could be shining or it could be nighttime. And I've even been able to describe myself. I am currently giving this lecture. Then when you're making a composite state, remember the number in front of each ket is the square root of the probability of being in that state. And finally, you can make measurements by completing the bracket and applying your basic rules once you know your orthogonal or mutually exclusive states. So here we're making measurements. We're asking questions like, what is the chance that my cat is currently causing trouble? What is the chance that dinner is finished cooking? What is the chance that my favorite sports team is currently winning? So that was Dirac notation. And it turns out that there are several very useful quantum concepts that you'll see showing up a lot in the work you'll be doing on quantum computing that we can express very straightforwardly with Dirac notation. So I'm going to be going into these here, into entanglement and some things related to phase and the Bloch sphere. So the first thing I want to talk about is entanglement. And if you've heard about quantum physics, you've probably heard of the term, but not necessarily known what it is. I think it's known as one of the more well-known kind of weird quantum effects. But once we have Dirac notation, once we know how to kind of write out a quantum state as an equation, it actually has a relatively straightforward explanation. And that explanation is an entangled state is a state where one object cannot be factored out. And to have an idea of what this means, let's start by looking at a not entangled state. So here I have a state of two cats, and an entangled state has to have two or more objects. And here there's a chance that one cat is eating and the other cat is eating, and one cat is eating and the other cat is causing trouble. And actually, if you look, remember you can multiply these. So I can actually factor out the behavior of the first cat from the second cat. And what this means is that these behaviors are independent. No matter what cat 2 is doing, cat 1 is eating. And no matter what cat 1 is doing, it's always eating. That doesn't tell us anything about what cat 2 is doing. Quantum states, on the other hand, are states where the behavior of the two or more objects completely depend on each other. So this is an example of an entangled state. In this state, it's two pretty mischievous cats. Whenever one is sleeping, the other one is off stealing their food, and vice versa. And so if you look at this, there is no common factor that we can factor out. Instead, what we see is that their behavior is completely independent. We may not know anything at the beginning, but we can just look at a single cat. And once we know what one cat is doing, we immediately know what the other cat is doing. If one cat is sleeping, the other one is eating, and vice versa. So this is entanglement. This is essentially, these states are entangled, they're interdependent. Their behavior depends on each other. So that's one of the concepts you'll be seeing very frequently. And the other one is this thing called phase. So if you remember back what I was discussing in the first section of this talk, I was saying that quantum states are waves. And we looked at some examples of how waves can interfere. And specifically, this was dependent on the phase, this offset between the waves. So how do we actually include this in our Dirac notation? Well, let's take our mealtime state and let's add something to it. So this is actually the true general definition for a quantum state, one where there are two possibilities. So we have our composite state, it's composed of our base states, and we have our probabilities in front of it. And then we've added this additional term. This is the relative phase, the relative offset between the waves. And again, if you're not familiar with complex numbers, don't worry too much about what exactly this is. Just know that it's kind of a cyclical term, kind of like a sine or a cosine, that can go essentially between 1 and -1. And also that when we take that square to do the probability, it completely cancels out. So this phase has no effect on the individual probabilities of being in one or the other of the component states, but one or other of the component states, but it still might have some other effects, as we've seen with interference. So let's take a closer look at this. Let's say we don't want to just have a mealtime state. Let's say we actually want to be able to describe what meal our cat is eating. So let's start by defining a breakfast state. This is a little more mischievous of a cat. So it's going to have a 50% chance of eating and a 50% chance of trouble. And so the question is, what can we introduce for a phase here that will not change these probabilities, but will be a different state, something distinguishable from breakfast. Well, one thing we could do is we could just add a -1. Remember that we're squaring this to get the probability. And so -1 squared is just 1. It's going to vanish when we actually take that probability. But this is also a different state from breakfast. Let's call it dinner, because this is a negative instead of a positive. That is something different. But the question is then, what did this actually do? What is the chance of being able to feed our cat dinner and breakfast at the same time? So using the language we've established of Dirac notation, we can ask that. This is saying if the cat is currently eating dinner, what is the chance that it is also eating breakfast? And we can calculate this using the methods we've seen. We take our breakfast bra and we split it into its basic states, the basic bras, and we do the same thing with dinner. And so then we multiply this through and it gives us 4 bra cat pairs. And remember our basic rules where the same state is 1 and different states is 0. So these two cancel out. Their 0 is shown down here. And these two are 1. And so now we put that together. We have 1/2 minus 1/2. It's 0. The chance of these being the same state is 0. So this is essentially destructive interference. Just by changing the phase, we have made it so these states have 0 overlap. They are orthogonal. Quantum physics tells us that you cannot eat breakfast for dinner. So let's take a little closer look at this. We can ask, how many of these orthogonal, these mutually exclusive mealtime states could we create? And it turns out that there are actually 4 phases that do this. It's 1, -1, I, and -I. And again, if you're not familiar with imaginary numbers, don't worry too much about this. Just know that there are 4 of these states. Quantum physics say that you can feed your cat between 1 and 4 times a day. And so let's take these 4 states and let's add them to our basic states. We called it eating in trouble, but to kind of relate this to the qubits you'll be working with, I'm going to represent those as 0 and 1. And we can actually put these together into a sphere. So at our North Pole, we have the 0 state, and on our South Pole, we have the 1 state. These are essentially our pure states. Everything else is some combination, some superposition of these. And then at the equator here, we have our 4 perpendicular states with their different phases. So we can represent that as these states at right angles to each other. And then every single point on the sphere is another state that we could make just by combining our 0 and 1, another mealtime state. You move up and down the sphere by changing the probability. States closer to 1 are going to have, closer to 0 are going to have a higher probability of being 0, and closer to 1 have a higher probability of being 1. And then you move around the state by changing the phase. And a single bit, a single cat that just has 2 possible states can access this entire sphere of possible states. And this is very different from classical computers. A classical computer can only access these 2 pure 0 and pure 1 states. And so this is where a lot of the quantum computing you're going to be learning about, a lot of the power comes from. We've seen that we can express much more complex states, many more possible states with a bit, and we can do many more things. We can have interference with them, we can have overlap. All of this is going to feed into quantum computing. And this sphere of possible states is known as the Bloch sphere. So what are our takeaways from this section? One is to remember the definition of entanglement. It just means that you have at least 2 objects and their behavior is dependent on each other. You cannot factor them out. And you'll get very familiar with states like this one, these entangled states, where the particle's behavior is dependent on each other. The other thing to remember is that quantum states can include a phase term. Essentially, the fully general definition of a state like this is one that has a phase term here. And finally, that we can show all possible states for a qubit or for any two-state object with the Bloch sphere here that shows the variety of states that this can actually take. So that is quantum physics. That is Dirac notation and what you will need to actually do your quantum computing work. And just to kind of sum up everything we just went through, I want to point out that quantum physics is different from classical physics. It's non-intuitive for just the way you usually experience the world around you. It's probabilistic. We can only state the probabilities of being in certain states until we measure it. Things are in a superposition until that point. The state is undetermined. It's in all possible states, and it's described by waves. And I also want you to remember that every physics equation is saying something about the world. And in particular, Dirac notation is expressing states of quantum objects. And so, for example, this talk is in the state of almost over. Finally, there are many quantum concepts you'll be seeing with Dirac notation, in particular entanglement, where two objects have their state dependent on each other, and the Bloch sphere, the way of expressing all possible states of one object. So welcome and good luck with all your work. I'm going to be in office hours on Friday if you have any questions, and please ask if you have questions. Asking questions not only helps you, it also helps me. It is not an imposition. It is how I better learn to teach you. And so it is very useful for me as well. And thank you for your time. Do we have time for questions or?
We do. I think that especially because it is our first day and some folks are having some issues getting on Discord. I would invite you to type your questions on the Zoom chat for now. If you have not been able to access Discord, and we'll have a couple of minutes of questions, and then I'm going to show you Discord and tell you where to click to accept the rules so we can continue our dynamic there. That being said, questions, preguntas, por favor, escríbanlas en el chat. Okay, Ruth Ann Martin has, how are the initial probabilities determined?
Do they mean sorry, this is making it nauseous. You mean when you're making composite states? So in this case, it's determined by observation. I'm trying to describe a cat that I've observed and measured things that way. In general, you're going to be defining states, or you're going to be adding things to doing things to states that will have well-known behaviors. So you'll be doing things like maybe starting out in a eating state, or you're starting out, for example, in a sleeping state, and then you'd be applying an operation to it, which in this case would probably be putting out food that would actually transform this state into a mealtime state. And so essentially, it's not, you'll be doing things that you know what probabilities you'll be applying to it. That is mostly what you'll be working with it, where you know the probabilities in advance and use that to define your states or use that to make your states.
Okay,
Ruth Ann, does that answer your question?
it does. Yeah, thank you.
Great, welcome. Okay, Christine Schoaf has another question. Are there ways to specific state transitions that are valid or invalid?
So yes, that's if what you're asking, I believe, is you're asking whether like eating state could transform into a sleeping state, that sort of thing. And whether you can specify whether this is allowed or not.
Yes, right.
Okay.
So sometimes states, you can't go from eating to trouble, but you can go from eating to sleeping.
Yeah, so Currently, the framework I've given here is not expressing how states transition. You're going to
Okay.
be working with something known as operators. So like, it will be something it's known as a hat because physicists have fun sometimes. It's something that operates on a state that transforms it into another state. And it's actually going to be the definition of the operator that tells you whether it can transform one state into another.
Okay.
That's something that I was not gotten into in this talk, but you will see that happen.
Mhm. Great. Does that answer your question, Christine?
Yep.
Wonderful. Thank you. Okay, Anthony Andino, in a superposition, does that mean that qubits can be on and off at the same time since we only see the probability of possible location? Technically,
Yes, that means they are on and off at the same time. They'll often be in something like this state until you actually measure it. And you'll actually see for the assignments you're doing, the way you will actually get an output is you won't have one output. You'll perform a measurement a lot of times. Like say if it was in this state, you would measure it 1,000 times and then it would tell you about 500 times you saw it in this state and about 500 times you saw it in that state. And that's how you can extract that. But before you do that measurement, it is simultaneously both.
okay. Thank you. Okay, someone, Anthony Andino, does that answer your question?
Yes, absolutely. Thank you.
Okay, you're welcome. All right, Hugo Christian Ojeda, what is the difference of pure state and mixture state? How to define each other?
So essentially, a lot of what this is based on, and let me try to get back to that slide. When we're talking about pure states, it's basically you select some number of states. If you're familiar with math, they're basis states. They're basically states that are mutually exclusive to each other and also span the entire possibility space. So example like this is in math, you'd have like the x-axis and the y-axis. You can define everything in terms of its position on x and position on y, and they're mutually exclusive. And so those are kind of your pure states. Those are your basis states. So in this case, for qubits, you can define everything in terms of the 0 state and the 1 state. And so those are your pure states. And kind of you set them up by definition so that they're orthogonal. But often you could choose different states in the same way that instead of choosing X and Y, you could have chose the diagonals. But for this specific situation, we're choosing 0 and 1, and you don't really need to worry about any other bases. You just use 0 and 1 for qubits.
Okay, Hugo, I am trying to find you here to unmute you, but I can't find you. Does that answer your question? If you can answer me in the chat. Okay. Thank you. All right, so Madhvyancha is asking Kevin, that was a great demo. I would like to understand the 11010 concept better. Also, why having multiple possible states for quantum computing makes it powerful. Oh, we'll get to that second question too.
Yeah.
That's the next level question, but yes, that's go ahead, Kevin.
Sorry, what was the first part again?
The first question was, Kevin, that was a great demo. I would like to understand the 11010 concept better.
Yes. Okay, so this is a way of kind of abbreviating states because it's kind of a pain to write out something like eating or trouble. And so what you do basically is you have multiple kets. This is kind of the original way we talked about doing this. Like this might be 3 qubits. So originally you would write it as multiple kets times each other. So this is qubit 1, this is qubit 2, this is qubit 3. But we can also say that you would basically always state this as 1, 2, 3. And so you can say that this is equal to just writing 1, 0, 1 in a single ket. And basically you're just collapsing it together to make it quicker to write and read. And you're just using the position within the ket to determine which qubit it corresponds to. So this would be 1, 2, 3 in a 3-qubit system.
Wonderful, Kevin. Thank you. All right. Do we have time? Okay, good. So that concludes our questions. Thank you very much, Dr. Bergman. We really appreciate your time and the creativity in which you walked us through this very complex topic. To the participants, the way that most of us have learned this has been with imagine some set of numbers or equations, between eating and sleeping and trouble, and that can be shock factor if you haven't seen math in a while. So I hope that this way of representing math has helped you on how to better grasp the concepts rather than trying to remember if linear algebra is something that was committed to your long-term memory. All right, so I'm going to share my screen here and just context shift for a moment. What I would like us to look at is the, actually, we'll get to the Discord channel in a second. I would like you to see the calendar. So this calendar is for this week, okay? And today we are in our event kickoff, right? So it's important that you join Discord for the live questions. Yesterday, you should have all received a welcome email. If you have the Zoom link, you received an email. It should come from Nydia@nluzstrategy.com, and it has instructions for you to be able to walk through, open Google Colab and understand how to open a file. This is critical because this week we're going to give you your first challenge, and don't worry, you will be prepared to pass that IBM challenge. And so we're going to give you an IBM challenge and a quiz. The due date here is Sunday at midnight. Please don't be late. And based on a passing rate of 70%, you will receive a competence certificate. Otherwise, you will receive a different participation. But I really urge you to try to focus on watching some of the videos. A lot of the terms that Kevin was describing, like Bell states and the different gates, we have what like little capsules of knowledge that, or you may want to call them qubits, quantum bits of information that our interns have just so arduously developed. And the intent behind this was that we all learn differently, and it is just so incredibly helpful to hear the same information. So repetition is key, hearing information from a different context. So there's someone else who presents, for example, Dirac notation, but he does it from a completely different aspect. And the way that he presents it is from a different aspect. There's a presentation on Bell states that was prepared by one of our interns also. And just so you know, we have a very international, very diverse team that encompasses multiple countries, multiple languages. And the idea was, how do we make this accessible for individuals that maybe math is not their language? So we don't have, not everyone's a physicist, not everyone's an engineer, not everyone is a mathematician. So for us, it's really important to provide to you diverse perspectives to aid you in your learning. That being said, ask questions on Discord. Let me go to Discord next. Oh, and so Kevin and a couple of us will be on our office hours on Discord on Friday. We're going to show you how to do that shortly. And then we're going to listen to our next speaker. We also have here office hours in, oh, that was my bad. This one is in Spanish. And this is just in case you want to talk to someone live, but we will be monitoring the Discord channel for the questions per week, because those topics, the topics that we're looking at this week are of a certain level of competency, and then next week we're going to look at the other ones. So let me share a different screen and walk you through this Discord channel. So you can make sure that you don't miss out. All right, so this is our Discord channel over here. What you'll see when you arrive, so you'll see this pink little Qiskit Fall Fest IBM logo, and then you'll be able to, if you are in the office hours, you don't need to be there or here. What you where you can come to is here in live questions and ask your questions here. The first thing that you're going to do is go to reglas if you speak Spanish, or rules, and you have to click this little check mark. So you either click that one and it's going to do that, and then we invite you to come here in live questions and just say hi. Great question. It's going to be EST midnight. All right. So in the welcome channel over here, you'll be able to see a couple of our bots, mostly our bots. But up here is what I want to show you. We have two events, and this is the event where we're going to have some Q&A in English, and here's an event that we're going to have a Q&A in Spanish. For those of you who are working, which is most folks, which is why we are having sessions at night, in the evening, or after business hours, we might be able to host a different session in English to help you with some of the basic concepts on Wednesday. If you feel it's necessary, we could do that also if Friday does not seem like a good day, Friday lunch. Okay, so here's your rundown. Events here in the top. When you come into the welcome channel, make sure that you accept the rules, and then you can go into general or live questions. And events does not seem to show anything. Okay, so Ayelen, can you double check her permissions to see what's going on there? And then great. The fact that you can both see here means that it should be open to everyone. All right, so that is our Discord channel. We are going to have the, this is Google Colab. Now, when we email you, or when we post the file in Discord, you're going to come over here and say File, Open Notebook, and it's going to be .ipynb. And this is how you're going to open it, okay? Just remember that. So when you're like, how do I open this notebook? You don't have an issue. And it's one of the main requirements here is that you have to go into IBM Quantum Learning and get your account open so you can start connecting through the API. So two things are going to be tested here. Can you replace? This is all the install instructions. Can you hit this little button to run things, right? And when you get to this section, this is not going to be the one you're looking at. So the API token, you're going to replace whatever's in here with your API token. It has pretty clear instructions, but I just want you to be able to walk through that so you don't have a problem. All right, in your welcome email over here, here is access to Google Colab, which should take you over here to the getting started, comenzando. If you are someone who's interested in continuing to learn more about Python and some of the different libraries that we're gonna just briefly look at today. We have videos that are going to take you in depth, but I recommend that if you want to do that and, you know, data science or machine learning is something you're getting into, use this as an opportunity and a platform where you have support and you're going to be able to ask questions about your installation. If you are an absolute beginner and you've never used this, maybe stick with Google Colab right now, and then towards the end switch, because it could be so cumbersome. If they do an update, you're going to have to reinstall everything, and it could be a little overwhelming to know whether you have a good response or a bad response, or if it's your setup that's not working. So if you're an absolute beginner, please go through Google Colab. And if you are also look into these videos, right? So we have a video in English and in Spanish, and it walks you through this IP and this Jupyter notebook. They're called Jupyter notebooks, and you should be able to open it that way. Okay, so what else? Let's get started with our next speaker. Sudikin, are you available at this time? Or do we have any questions in the chat? ¿En dónde está explicado el cambio de IT? I can also not see events. Okay. Yes, this recording would be available after this. It's just we need some time to clean it up and post it. Probably by Friday, being realistic. And Gabriela pregunta dónde tenemos que cambiar el ID. Okay. Those questions about how to change your ID in Discord, Aileen, if you could put some instructions on Discord on how to do that, that would be great. Okay, so Dickon, are you ready? Let me give you a spotlight. Go ahead and unmute. Okay, so Dickon, can you, are you audible? All right, so he is having some connection issues at this time. So what we are going to do is that we are going to share his presentation here. We have planned for this. Okay, so first and foremost, I'm going to introduce him. And then we will get started and hopefully we'll be able to. Okay, so Sudikin Pramanik, he holds a master's degree in physics where he focused on solar flare perturbations. Driven by his passion for teaching, he went on to earn a bachelor's degree in education and has 11 years of experience teaching physics, mentoring several all India rankers. He's also pursuing an master's in technology and geoinformatics at the Indian Space Research Organization as a Golden Jubilee Scholar. Additionally, he holds an all India rank of 30 in the graduate aptitude test of engineering. During his MTech, he is assessing quantum computing algorithms on Earth observation data, and he possesses deep knowledge in quantum physics and geophysics information systems. So he is a very talented speaker, and we are asking him to walk you through one of the most complex topics here, which is how do we translate the world around us before you can even talk about coding anything in classical computers or quantum computers? Do you truly understand the basis of data gathering? How do you translate the world around us into data, into numbers, into something like the 4 seasons of the year in the northern and the southern hemisphere are 4 different data points, and what does that look like? Are they, equally timed? How do you do that? And what does it look like in code? So he's going to walk us through an example that hopefully will simplify this, because it is the basis of understanding how to bring that into proper data translations. And then if we get time to look into this further, we're going to run into some of the Python libraries. But for now, I'm going to play Sudikin's presentation, and then we are going to move into some Q&A with him. All right.
How are you? I hope all of you are doing fine. I am Sudikin Pramanik from INLUS. I come from India. I have a master's in physics, bachelor's in education, MTech in geoinformatics from Indian Space Research Organization. Here, I use quantum computing for feature extraction on Earth observation data. I have been a teacher for over a decade. I teach physics, mostly high school and undergraduate physics. I love to stay among students. I'll be your guide and friend for today. I'll be helping you out in understanding a very complex topic, which is translating the world around us to data and strategies to algorithms. It's a technical exploration. I thank INLUS for giving me this opportunity to help you guys out. Without wasting much time, we'll directly delve into the topic. So our topic is divided into 4 parts. We'll go in each part with a detail, but keeping in mind that as most of you may not be from this background, you may be having problem in understanding them directly. So I'll be using some analogies so that you can understand it in a proper way, yet I'll be delving into some deeper topics also. Okay. So first is how data is as a representation of the world. So how we see data in our surrounding. So in this thing, we'll learn data acquisition, data pre-processing, and data representation. So let us understand data acquisition. So how about we make some food? All of you love to make food? Chalo, let's make some food. How about a simple potato dish? But first thing for a potato dish is what? We need a potato, right? So we need a potato. So from where do we get potato? Farms. Similarly, to do anything with data, first thing is we need data. So where do we get data? So how can we collect real world data? Think of a sensory device that you have since birth which can collect data. Think. Right. You have your eyes which can see, your nose that can smell, your skin that can feel, and your ear that can listen. We all know this, right? So what type of data are they? Okay, to understand that, we have to discuss more on it. Let's take for an example our eye. So what do we have? Light enters through the lens and falls on the retina. Then what does the retina do? The retina has photosensitive cells. What are photosensitive cells? Cells that responds to the amount of light falling on it. Okay, because it is sensitive to light. Those cells are known as rods and cones. Now these photoreceptors convert the light energy to electrical energy. Then what happens? Then these electrical energy are actually electrical signals which we may as of now call as analog electrical data. They are transferred to brain. The brain stores them in neurons as synaptic strength. So what did we understand? Light enters from the lens, falls on the retina. Okay, this is the black spot. It falls on the retina somewhere. Suppose it falls here. Now here it is converted to electrical signals. These electrical signals pass to the brain and it is stored somewhere in the brain. Okay. Now let us understand what happens in a satellite, because I am mostly working on satellite data. So let me explain you what happens in a satellite. So light falls from the sun on an object. It gets reflected. Now the satellite catches this light. Then what happens? So light falls on a satellite sensor. What is a sensor? Anything that receives the data is a sensor. Anything that can understand the data is a sensor. Okay, suppose our light is falling on it, something is able to understand what is falling on it. That something is the sensor. So it is then converted to analog signals at the sensor output. So suppose this is a sensor, light falls on the sensor, sensor gives you a output. Okay, now the output falls on an analog to digital converter. It converts the analog signals to 1 and 0. All of you know, then it goes through a analog to digital converter. Then we get only 0 and 1 and nothing else. So we get an analog signal that falls on a sensor, passes through a circuit, gets only 0 and 1 in the output. Then it is transferred to a memory device where the presence or absence of electrons ensures the stored value as a binary memory. So then what happens? There are various ways of storing our data. So one can be by the absence or presence of an electron, meaning a 0 or 1, then can be stored. All of you know this thing na, that flash drive, hard drive, memory drive, like these are the various storing devices. Okay, so data can be stored there. Okay, now what are the various types of data? There can be geospatial data, financial data, temporal data, multimedia data, biometric data. What is geospatial? It has geography, that is geographical and spatial data. What is financial data? That relates to money. What is temporal data? Relates to time. Temporal data relates to time. What is multimedia data? Your audio video data, the videos that you see, the music that you hear, they are multimedia data. What is biometric data? Data relating to human bodies or any body parts. That is biometric data. Now you have got the data. So suppose you went to a field, you picked up some potatoes from the field. So how is the potato? The potato has the potato bulb, then it has the leaves with it, right? Now suppose you want to make a dish of potato. Can you put this whole potato and eat it? You cannot now. So now we have collected data, that's fine, but can we use the data as we have collected? It is like you have picked up a potato from a field, but can you eat it directly? No, right? So you need to wash it, peel it, remove any unwanted portions. This is what is similar to data preprocessing. So what you did is that you took the potato from the field, you processed the data. Okay, you processed the data before actually using it. That is the pre-processing. So data pre-processing is a series of operations to ensure that raw data, what is the raw data? The initial data that the satellite has taken, to become usable for algorithmic modeling. So we want to do some process on the data, right? Now in pre-processing, we'll use that end part of the satellite data, then we'll do some cleaning and stuff on it, then we'll get a processed data, right? So what are the various things? That can be data cleaning, that is handling missing data, removing some noise, doing normalization, standardization. There can be data transformation where we do encoding of a categorical data. There can be range compression. There can be feature selection and dimensionality reduction. What is dimensionality reduction? See, suppose I have a satellite data which is having 250 bands. Now to process the 250 bands is very difficult for a normal computer. So we need to reduce the number of bands, yet we need to understand that when we are reducing the number of bands, it should be such that we don't lose a major part of the data. So we do feature selection and dimensionality reduction. Then we do data augmentation, then we do data integration. These are the various processes in which preprocessing can be done. Now we have taken the potato from the field, we have cleaned the potato. Now what is the next step? Shall we directly put into the oven? No, na. Suppose I have a bag of potato. What do? We store them. So that is the data representation. So now we have cleaned the potato. How do we keep it for future use? Yes, we can store it as a whole in a shelf, or we can store it in bulk in a large sack. So which is better? Storing in a shelf is better, or storing in a large sack is better? So what happens is that we can separate different sizes and sort them accordingly. Suppose I have various kinds of data. I can sort the data and I can keep it accordingly. Or shall I put everything in a sack and I keep it? If I keep it in a sack, putting everything together, will it be easier for me to find out a specific kind of potato if I need it? Suppose I am making a dish, I need small potatoes. I am making another dish, I need big potatoes. If I keep it in a sack, it will be very difficult for me, right? So we would like to keep it in arranged orders. Similarly, we need data to be structured, formatted and organized so that in future it becomes easier to process using algorithms and models. So we also need to keep the data in such a way, arranged in such a way, so that when we need the data in future, we can take the data directly without much hassle. Okay. So we understood what we do when we find the data, process the data, pre-process the data, and we keep a representation of the data. Now, there are some methods of representation. They can be tabular data, sparse representation, graph representation, time series representation, image representation, and vector representation. Okay. Now let us move into part 2. So we have got the data, we have cleaned the data, we have kept the data aside. Now we are looking at strategies as computational models. So what are they? First is algorithmic design, machine learning, then hybrid model. So let us go into algorithmic design. So what is an algorithm? So now we have our potato. We need to process them so that we can get a desired food or a craft. Let's talk about food. Now how can I transform the potatoes in a product? Shall we go with any unknown technique or shall we experiment with the unknown? So shall we go with a known technique or shall we experiment with the unknown? I need to make mashed potato. So what do we do? First we hear from our elders or from a recipe, how have that been made earlier? So that we can get an idea, or we need to follow the steps. So to do this, we need to determine the various methods. Similarly, for data, these methods can be deterministic or stochastic. Okay, so now we'll understand what is stochastic data, what is deterministic data. First, understand deterministic data. Deterministic data follows a strict recipe. Suppose you want to make mashed potato, someone has written a recipe, you do everything what is stated in the recipe, you follow every steps. Okay. What is a stochastic method? It's like adding a bit more of clarified butter to see if the recipe tastes better. Like you want to make mashed potato, you are not following a recipe. You are trying with the recipes. You are putting sometimes more amount of butter, sometimes more amount of chili, sometimes no chili. So what you are doing is you are not following a recipe. You are randomly doing things, yet you are doing things in a way that will be meaningful. Okay. So as an use case for deterministic method, using predefined algorithms like sorting and modeling. So for data, we can have predefined algorithms which are already said, trusted, proven, and then we can put our data and find out something. So they can be like binary sort, quick sort. Okay. Now for stochastic method, we can incorporate randomness in the decision making process. Like we can do optimization problems like genetic algorithms, simulated annealing, or stochastic algorithms like Markov chain and Monte Carlo simulations. Okay. Now our second portion is machine learning. Now I think most of you have heard this thing about machine learning, right? It's a very buzzword right now. So suppose you have Parthiv as a customer who wants mashed potato with a lot of chili, and you have Niloy as a customer who wants mashed potato with very less amount of chili. Now it is not mentioned anywhere in the recipe what to do for such customers. You have a recipe, but you don't know what to do when a customer suddenly asks and tells you a new thing. I want more chili, or someone will say, no, I want very less chili. What will the chef do then? So what the chef does is he learns from the feedback. So first he will give Niloy 1 spoon of chili in his mashed potato. So Niloy eats the mashed potato and says it is too hot. So what will the chef do? Will he increase the amount of chili because Niloy does not like chili? So what the chef will do is he will decrease the amount of chili. So what should the chef do? The chef will decrease the amount of chili. Yes. So he will decrease, say, to half spoon. This is how the chef is learning each time from the feedback of the customer and providing forward food with new adjustments. See, he's very happy, right? So now I hope you think of what to do with Parthiv. Now Parthiv likes more chili. What to do? Yeah, he'll again put the half amount of chili. Parthiv will say, no, this is not at all hot. I need more chili. So what he'll do? He'll put more amount of chili and more amount of chili, and every time he'll take the feedback of Parthiv unless he is satisfied. So similarly, for data based on machine learning, we can learn pattern and relationships from large data sets. Okay, there are patterns in data. Machine learning learns those patterns in data by giving forward and backward inputs and output. Okay, so there can be popular machine learning techniques like supervised learning, example SVM, unsupervised learning like discovering pattern from unlabeled data, reinforcement learning, that is learning through interactions with environment and optimizing strategies. Now let us look at this picture by our side. See, can you tell me what will this dark blue portion represent, or this yellow portion represent? See, all the dark blue portion are classified as water. It is done by machine learning technique. All the yellow portions are cropland. So machine learning is very capable in figuring out information from the data. Now let us talk about hybrid model. So what is hybrid model? Now suppose the chef knows that Niloy eats less chili in mashed potato. We remember Niloy? Just we talked about Niloy. So Niloy does not like chili. So he eats very bland food. Now he wants potato chips. The chef does not have a potato chips recipe with a less chili. So what will the chef do? Chef will have a recipe of potato chips. Chef will have an understanding of Niloy. So he'll combine both of the knowledges and will produce a hybrid approach. So what does it mean for data? It means that many systems leverage a combination of deterministic algorithms and machine learning models. For example, in a recommendation system, content-based filtering algorithm may be used in combination with collaborative filtering model to recommend products based on user preferences and behavior patterns. Okay. Now, so what did we do? Let us do a brief review. We got data, we processed data, we kept the data. Then we took the data, we used some algorithms, and we used some machine learning models to find out some information from the data. Now, how about the complexity of getting those results? So what is complexity? Complexity means, suppose for time, how long duration it is taking. Suppose for space, how much memory space it is taking. Parallelism, how fast it is happening, or how many parallel things can you do together with the data. So let us talk about time complexity. So now let's talk about a business firm who wants a mass produced chips. Now suppose to complete one batch of, he needs a time of 6 hours. So he can produce a maximum of 4 batches in a day, because 6 hours 24 by 6, that will be 4, right? So he can produce a maximum of 4 batches of chips. So how about he has developed a process in which he can complete one batch in 2 hours. That means 24 divided by 2, that will give 12, right? So if he can somehow reduce a process in lesser amount of time, he can do more work within his time limitation, right? That is how beautiful is time complexity. So in case of data, what does time complexity mean? It means that the computational cost of an algorithm is typically expressed in terms of time complexity, often denoted by big O notation. The time complexity quantifies how the running time of an algorithm grows with size of the input. See, you see this red thing, and it is steeper, right? That means how steep your curve is, it is more complex, and how flattened your curve is, it is least complex. So there are various types of complexity algorithms which can reduce the complexity time based on an operation. Now what is space complexity? Now a new batch of potato chips has come out. So shall I store it in sacks on the floor? I have made a finished product. I have made a bag of potato chips. So how do I store it? Just imagine how much floor area will it take to store it in sacks. So I am storing in sacks. I don't have racks, I don't have anything. I am just storing it in sacks randomly. Is it a good idea? Don't you think it is more economical to have less space for storage? Right? So I have lots of sacks. I have not organized that. I don't have any racks. All sacks are lying on the floor. I have thousands and thousands of sacks. Is it a very good idea to keep the sacks in that way? No, no. That is space complexity. So what does it do? Space complexity refers to the amount of memory required by an algorithm relative to its input size. Optimizing space complexity is crucial in environments with limited computational resources such as embedded systems or mobile devices. In mobile device, how much data can you get? 256 GB maximum. Usually you get around 128 GB. So if the space is not optimized, what will happen is that it will use up a lot of space, and that won't be in a good spot for you, because you will keep on buying new memory cards or new phones or deleting data. That's not a good thing. So we need space optimizations. Now what is parallelism? So understand in this way that suppose a batch of potato needs 50 minutes to bake. One batch requires 50 minutes. Now however larger machine or better machine you take, you cannot reduce the frying time. That is fixed for a potato. You can, for packaging, for processing, you can do a lot of time. You can reduce the time, you can do things, but for frying of the chips, 50 minutes is required. You cannot reduce that. Now it will ensure that the chips won't be fried properly if you reduce the frying time. So what shall the businessman do? So he can modify his instrument, but he cannot reduce the time. So what he will do is that he'll set up many small manufacturing units in place of one large unit, so that he can fry more chips parallelly in a small batch, ultimately gaining a large volume. So what he'll do, he'll not make a very big machine. He will make small machines. All of the machines will take 1 hour, 1 hour, 1 hour, 1 hour for the potato to fry, and he'll make many batches of potato. At the end, he'll collect all the potatoes and make a small and make a large volume from these individual small volumes. In that way, see how many number of batches he's making, how fast it is happening in terms of volume, though he's giving small batches in small parts. This is parallelism. So what is parallelism? We usually take a task, do one after the other, and get the solution. What he is doing is that he is breaking the task into small portions. Then they are processing the same step, and then ultimately the entire collection of the result is his final collection. So MapReduce, for instance, is a distributed algorithmic framework used in big data environments to process large data sets. Similarly, GPU-based computing is often employed in deep learning to accelerate matrix operations via parallel execution. I hope you have heard about NVIDIA. What is NVIDIA? NVIDIA is using GPU computation. That is, he is distributing the task parallelly and getting the result much faster. So now so let us recapture what we have done. We have taken the potatoes, we have cleaned the potatoes, we have organized the potatoes. Now we made a recipe with the potatoes, we made a batch out of those recipes, and we have stored the batch. We have also seen how to reduce the time, how to reduce the space, and optimization things, and we have also learned how to make the process faster. This is what we have done till now. Now we have our batch of potatoes ready. Then what to do? Will you keep the potatoes with yourself, or will you try to sell the chips? Will you try to sell the finished products? This is what is translating outputs back to the real world. So we take things from the world, we do something, we give it back to the world. So first is visualization. Suppose in your industry you make two varieties of chips. One is classic salted, one is onion flavored. Now you have packed them. Suppose you pack them in this way, which has no labels, nothing, just a transparent bag. Do you think it will be easy for your customer to understand which variety of chips it is? Will it be easy? Will he be able to understand? No. So your sales, will it go up? No. So you need to represent your results in such a way that it becomes easier to understand for your target buyers. So suppose you have a onion flavored chips and you have a classic flavored chips, and you have different packaging, so the customer will easily understand and pick up his desired results, right? So in similar way, output of a data is usually numbers. So how will the spectator understand gigabytes of numbers? Like so many numbers, you cannot understand directly from numbers. So data visualization techniques such as heat map, scatter plot, 3D graph help in summarizing and between complex data structures and model options. So see this is the back of image. It shows that where the price of electricity is high is marked in a deep dark color. So see this region is having higher electricity price, this region is having lower electricity price. Okay, now actuation. What is actuation? So you have a nicely packed product. So what do you do now? You sell them, right? So you distribute and sell your product. You want to deliver the product to the actual customers. That is, you want to see the implementation of your product. So you give them to a grocery store, restaurant, online store, so that your product can be utilized to the ultimate goal of making it. So you are making a chips, you want to sell the chips. So you give them to the grocery stores, to those places. Similarly, you made a result, you made a pre-processing, you made a data. Now you need to see the result of the data. Suppose you are working on robots. So what you will do, you will feed the data into the robot so that the robot does some work and you can get the result from viewing what the robot is doing. So this involves implementing changes, triggering events, or initiating processes based on the analysis of data. In systems involving physical components such as robotics or industrial automation, the final step may involve actuating physical devices based on algorithmic outputs. In such cases, control algorithms translate high-level strategies goals into real-time actions for motors, sensors, and other hardware components. So we understood what is actuation. So the robots will behave, we'll understand from the movement of robots that what we desire to do, have we been able to do that in the way we wanted it to do? Next is decision support system. Now this is very important. Decision support system is very important. So what is it? So your chips are sold. The stores are placing orders for more amount of onion chips than classic chips. So what do you understand? So you understand that your demand for classic chips is less than the onion chips. So tell me, in your production line, which chips shall you produce more? Onion chips. Obviously, because people are liking it more. Or after some times you find that, let us go to the chef example. You find that Niloy, who used to eat very less amount of chili, now is asking for more chili. So what do? Shall you still give him less amount of chili in mashed potato? No, no. You will increase the amount of chili. So you need to take decisions. That means you need to have a decision support system that will analyze and produce decisions based on your informed analysis. In the similar way, in decision support system, for real world data translated into the machine data, decision support system incorporates model management systems that simulate the real world systems to enhance understanding and identify improvement opportunities. So what to do with the data? What the decision management systems tells us that which things to look into, which decisions to take, which are the correct ways of handling things. So organizations utilize these models to predict how outcomes will shift with various adjustments, particularly for complex, costly or hazardous systems. So they cannot be fully explored in reality. We have various techniques of MCDM. What is MCDM? Multi-criteria decision making. We have algorithms like HP, TOPSIS, which help in fulfilling the decision requirements. So in conclusion, the journey of the potato from farming to the finished product, I hope it explains in a very easy way, parallels the process of translating real world data into data and algorithms. So I hope the analogy I used was able to make you understand the topic in a much easier way. So each step from cultivation and harvesting to processing and distribution reflects the complexities and strategies involved in creating actionable insights from raw data. So ultimately leading to a product that meets customer needs and preferences. So I hope you understood what I have tried to tell you. Thank you. I have been very happy being able to help you all. Looking forward for more events to come. Stay connected. Bye bye.
All right, so that was Sudikin. I'm going to unmute him here and give him a spotlight. Great presentation, Sudikin. Thank you so much. I'm glad we planned for some some connection issues, so here we are. Do we have any questions for Sudikin? Let's see. I hear current speaker is absolutely a great teacher. Can someone please remind me his full name? Yes, Sudikin Pramanik. And do we have questions for him? Let's see, part of the presentation. Eileen, I'm going to ask you to unmute if there's any questions in Discord that you can read them, please. Okay.
Por el momento no hay ninguna.
No, okay. We just have a lot of compliments here, Sudikin, for you. So you either extremely clear, but great presentation. Thank you, Sudikin. Okay, so are we expected to beef up on knowledge in LLM to be successful with this course? So this is a class for multiple levels, so a lot of people may not have that level of understanding of data. And the idea is that we want people to be able to hit the ground running, because if you don't know the current limitations of processing data today, you won't know where there is a quantum advantage or a potential quantum advantage, or the situations in which quantum computing is making things faster. But Sudikin, can you talk a little bit more about like your experience with that fine line between where you see some advantage?
For LLMs, it's very useful right now because suppose I want to do some geospatial processing. So if my end person who is using that is not that much advanced in technological aspects, like we use ChatGPT. So when we type something in ChatGPT, we directly get an answer. Now the person who is typing in ChatGPT, like a person, for example, me, I may not be sound in many different topics except the topics that I know actually. So how do I get the answers from there? So as I'm working on satellite data, I would like to tell it in this way. Many people may not be aware of how the geostatistics or its algorithms work in finding out a result from a satellite image. So suppose I have built up a system in which I enter a query, and suppose I'm a farmer, I just want to know which crop should I harvest in the season of April. Then I'll just type which crop should I harvest in the season of April in India. Simple. Then if I can make a geostatistical model based on LLM, then we can find out a result directly, and the LLM will just give out a result that you can harvest the crop of, suppose, ragi. So this is the benefit LLM has right now, and it is being explored. We are already having a project which is going on. It's a government funded project about 20 crore rupees. Right now it is going on in ISRO, in where I am staying right now. So they are working on it. It's a very challenging task to incorporate so much data and do a geoprocessing live using LLMs. So yeah, LLM is a very important aspect in terms of data processing tasks, in terms of making things work out easier. So yeah, I think it explains.
Thank you very much, Sudikin. And so I have time for maybe one more question, and then we're going to start wrapping up. So is there any questions on Discord, Ayelen? No? Okay. So today the goal was to give you the basis of just go over the basics. There is a lot that we are going to also cover for the for you to understand qubits and different aspects of quantum computing. So what we're going to do is we're going to be sharing with you a couple of different assignments and a couple of different videos that will help you understand, kind of just confirm the concepts that were described, but in a different way, right? This is more of the classical IBM way of explaining a classical bit with a coin flip, or understanding whether the state in the block sphere is 1 or a 0. And so you'll be able to go through some of this information. You have here what Kevin explained, and for these classes, right, we're going to work with numbers, assuming they're all real numbers. We're not going to be working with the complex numbers at this point, but as you get deeper into it, you will be able to see that. So just briefly to show you here that the difference with quantum computing is exactly here in 0, 1. Oh, I wasn't sharing presentation, sorry. So that, you can have a 0, 0 state and a 0, 1, right? Heads or tails. But in quantum computing, there is a state that could be here, where you are, in the 0, 1 and in the 1 zeros. And that's not necessarily correct, but it's important for you to kind of know that that is how, that is where that new, that small detail is in being able to calculate probability. So what is quantum computing? In quantum computing, what we're doing is we're trying to shift probabilities. And when we are shifting our probabilities, we want to be able to see in superposition and interference, how can we maximize that? The probabilities of something being 1 or 0. For that, we're going to apply different gates. And we'll talk more about this, but this is really what a quantum circuit looks like. Here's a Hadamard gate. I'm going to send a video on that, and then we're going to talk about it next week. There is no homework on that. It's just important for you to listen to it. I don't want to start running something else that that's going to put us over time. And then this is an X gate. These things are measurement. And one thing that it's important for us to understand is that we are reaching the era of utility within the quantum space. And what that means is that the hardware is catching up, where we're going to be able to get additional speed up for, I'm not sure what's happening there, but we're going to be able to find interactions here. Now, Shor's algorithm is one of the most famous right now because it's related to RSA encryption. We're going to review that very briefly because our focus isn't there, but the ability to, for example, currently break that algorithm is somewhat of a misnomer, because the hardware needs to catch up on how it could, break that encryption. And it's trying to find the factors that make up a multiplication. So the bigger the numbers, the more, processing computation you're going to need. But what this is trying to explain is that we're getting to a place in quantum computing where we have more useful applications of things. And so this is what a quantum computer looks like. This is what the IBM systems that were shared with us look like. This is apparently an IBM computer that is in a cafeteria of a building. And this is the latest one that has been created. I cannot remember the name, but the Heron qubit is what is being operationalized right now. Now, the other thing I'm going to show you is pretty much your assignments, because we are at 9:59. So in this section over here, you're going to be able, let me share where your assignments are going to be. So we talked about a graded notebook, a challenge notebook. And before we go through that, I want you to know that for us, it's important that you actually use ChatGPT. Use ChatGPT, make sure that you understand how to discern the output of the AIs, whether you use ChatGPT or Gemini or whichever you wish to use. Just make sure that you use it responsibly and that you understand things that you're doing. So here in week 1, we're also going to share this in Discord, is going to be the quiz from 0 to I'm here, the basics, right? In terms of the Python content, I'm going to send the recordings, and we're going to have an extra office hour where you can come and ask questions about the recordings dedicated to just that, since we don't want to keep you over time. And then your attendee guide that I reviewed is here, and I'm going to post the challenge here also and in the Discord channel. So just as a reminder of what we have to do today, we are going to close the session, maybe give a couple more minutes for questions, but if this is a hard stop for you, you can drop. Make sure that you ask questions on the Discord channel. And again, the section for the questions here is going to be week 1. Let me find it and pull it up, because we want you to know where to ask questions. So, Ayelen, if you could post a link to that, I'm just going to share it one more time to show them where it is. Go into it. So week 1 questions is under Comunidad. And so, we were right here with the live questions. And week 1, Marius kicked us off here. And so anything you have in terms of the assignments, the videos, I will be sending a little package for you all as we transition off of email and into Discord. This is where you should be asking all your questions for the assignments this week. And please make sure that in your quiz you use the name and the email that you signed up with, because those are the names that are going to go out with your certifications. And again, when you join the office hours, you just click here, office hours, or you go to the top and you click on events, and you should be able to see them. And then you could just join office hours. But if you have any issues with joining, just ask us in week 1 questions, and we will help you do that. So expect the IBM challenge notebooks. Remember, you have to go into Google Colab and open it, right? Are there any questions right now? All right. Okay. In case you are concerned that the IBM challenge is hard or whatnot, it's pretty much for you to make sure you have access, ensure that you understand the basics of code, like commenting what is a function, what isn't, and that you are able to run the cells to install things. If you do not insert your API token and you multitask, you will need to rerun the install section. So in case you're having problems, just remember to do that. The drive link is in the welcome email where it says, I think, getting started, comenzando. If there are any other questions, we'll be here for a couple of minutes, but otherwise, I know that there are some folks that are on earlier time zones and later time zones. So we are going to post the video probably Friday. Just be on the lookout for information both in your email and in Discord just for this week, because we're transitioning everything to Discord. Thank you for your time and your willingness to learn, and to our fabulous speakers, co-organizers, and group of almost 40 plus, almost 50 people working to bring this to you. So have a great weekend, and we will be in touch. Ask questions, please. If you are about to quit or this seemed too complicated, make sure that you ask for support in the group, because that's what we are here for. All right. Wonderful. Stay on for a couple more minutes for any questions, and I'm going to just stop the recording.